Then we can go ahead to Daniel's presentation on 5G clarity innovations beyond 3GPP release 16.
Hi, Mir. Good morning, everyone. Let me see. Do you see this
Full screen,
the
yes,
slides in full screen?
Yep,
Okay.
yep.
So, hello, everyone. My name is Daniel Camps. I'm with I2CAT in Barcelona. And I'm also the technical coordinator of the 5G Clarity project. And so the intent of the call is to give you a deeper insight into what are the main innovations that we are trying to bring from the Clarity side on this beyond 5G vision. Okay, and let me start by giving you an overview of the project. So the project basically focuses around private networks, and as Jose indicated at the beginning, we have this notion of private networks that can also be a multi-tenant environment. So this is one important aspect in our vision. A second important aspect in our vision is that we consider a multiplicity of wireless access technologies to be part of this private network, namely cellular, 5G and R, obviously, but also Wi-Fi and Li-Fi as well. And the third, let's say, leg of innovation in the project is that we are looking into artificial intelligence, and we're looking into what we call intent-based policies to ease the manageability of this network. So this is a bit tapping into one of the topics that was mentioned before in the chat about who will manage these networks, operators, verticals itself, etc. An overview of the partners. So many of them will look familiar to you. So, well, project is coordinated by IHP, Gigasys, and I2CAT. We have Telefonica and vendors like Ericsson and Interdigital. Some European and UK SMEs like Accelera and Pure Leafy. We have a vertical, an OT player like Bosch with a factory in Spain, and universities in the UK and in Spain. So let me start with what motivated the project. The project, we submitted our bid, I believe, in 2019. And it was already clear back then that the momentum that private networks were gaining. But we saw several important challenges there. So first one is that they are not greenfield environments. So there is already deployed technology, especially based on Wi-Fi and IEEE 802.11. So it's very important that whenever we go and deploy 5G, it's not like an add-on that it's completely separated from what's already in there, but that we can incorporate the technologies that were already there. The second aspect is everything that Jose discussed and presented about the interaction of public and private. Okay, there's here obviously many open challenges that need to be addressed. Third item is related to the manageability, how to make it easy to operate, lower the bar on the operational burden of these networks. And then the fourth, let's say, specific challenge is there are some use cases appearing in MPNs that are not so or have not been so relevant in public networks. For example, the indoor centimeter level positioning, which is a requirement for many of the factory applications. So how do we, what's our approach? What's our proposal to try to address these challenges? So we have innovations in different areas. First one is the Li-Fi technology. So I will be explaining later on how do we make use of Li-Fi. But Li-Fi has certain, let's say, inherent properties like security, because it's a very focused, the light is very focused beam. And also it can help in positioning, for example. The second, let's say, innovation pillar that we have is we want to make a smart use of the various wireless technologies. And by making a smart use, what we mean is that for some applications, you might want to aggregate all this capacity. For some other applications, you might want to replicate and send redundant packets. Okay, so is this making the best use of the aggregate technologies for each application? And we are developing what we call a multi-connectivity framework for that. Then the centimeter level localization and synchronization capabilities that come about through combined use of the different technologies. the AI and intent-based network management that I explained before, and the combination of private and public networks. Let me start with giving you a bird's eye view of the architecture that we put forward in the project. Following the 5G principles, so we have a decoupling between physical and virtual network functions. So in what we call the infrastructure stratum is where our physical network functions live, where we have the access nodes, okay, from each of the different technologies. And we have two different compute clusters. We have what we call the RAN cluster that is hosting RAN-related network functions. And here we follow the ORAN specification. It was also asked in the chat, the role of ORAN in private 5G networks. We see it's going to be a relevant technology for private 5G because the compatibility between radio heads and BBUs that are required in these environments is more developed. And also the Open RAN opens opportunities for innovation, for building customized functions in what they call the RAN intelligent controller. And these customized functions can be key differentiators for some of the NPN use cases. And then we have another compute cluster, what we call the edge cluster, that is hosting the core network or parts of the core network if what we are thinking about is a PNI NPN use case, and then the applications that services that need to run on premises. Besides the infrastructure and the virtual network stratums, we have a management plane, okay? We need a management stratum that is going to manage these physical and virtual network functions in order to allow the operator to configure all this infrastructure and be able to slice it, okay? So remember at the beginning, I mentioned that we intend to support multi-tenancy, for example, in stadiums, as it was mentioned before, where we could set up different infrastructure slices, one for the private venue owner and a second one for an operator that wants to extend coverage, for example. So all this is enabled by the management and orchestration stratum. And on top of all this, we have what we call the intelligence stratum that's composed of an AI engine, which is an execution environment for machine learning models, and an intent engine that is a software platform that is going to expose very high-level intent-based interface towards the machine learning models and the network operator and hide all the complexity to manage this infrastructure. So let me now go into samples, okay? A bit more detail into the different innovations of the project, namely the multi-connectivity, the slicing, and the positioning. And at the end, to conclude, I will explain you how we apply these technologies in the different use cases that we have in the project. So starting with the multi-connectivity framework, what this figure represents is basically a network diagram of what an NPN could look like. So we have the edge cluster that is hosting the 5G core and the services, and there is a user plane function, okay, inside the edge cluster. It's all the traffic that comes from the applications has to go through this user plane function. That's on one side. Then we have the radio devices that we have 5G, we have the Li-Fis and the Wi-Fis, and then we have the user equipment, and in particular, we can of course have 5G only user equipment, Wi-Fi only user equipment. But what's most interesting to us is to consider the fact that you can have user equipments that combine the three wireless technologies, okay? The 5G, the Wi-Fi, and the Wi-Fi. So the idea is that we develop the means and the functions that allow this UE to decide how it's going to send a given data flow, okay, between an application and the UE, how it's going to balance this flow through the different technologies. And to do this, we use a framework that is being specified by 3GPP that is called AT3S, okay, Adaptive Traffic Splitting, Switching, and Steering. And based on these technologies, we are developing our smart connectivity solution that will allow what I explained before. So we support a redundant mode. So imagine we have an application that has high requirements on reliability and low latency. So what we can do is this UE can classify this application and it's going to decide to repeat every packet that comes from the application through the three interfaces. So the first one that goes across the network is the first one that's delivered to the applications, the other are discarded. With this, we increase reliability, we decrease delay. We have another application, for example, that what it wants is it's capacity hungry. So this one is going to aggregate the different wireless technologies. So, and this is interesting because we can have Wi-Fi 6 providing a lot of bandwidth at the moment, even more with Wi-Fi 6E, where you're going to have 160 megahertz channels available in the 6 gigahertz band. And then you have the N77 in the UK, for example. You guys have the 100 megahertz, for example, carrier in the N77 band. So that could be a very powerful wireless bandwidth by aggregating these different technologies. And then we support a third mode where we allow to, let's say, we allowed an external function that we say it can be a machine learning model to decide exactly how many packets should be flowing from each of the technologies. So we enable this application and external control or policy about how traffic has to be balanced. Another aspect related to the multi-connectivity framework is, and especially when we're thinking about machine learning models, is we need data, okay? We need data, we need to understand how the network, the telemetry, the signal that the UE is receiving from the different technologies, and how can you gather such data? Usually these technologies are closed, are proprietary, so it's hard to extract the telemetry that such advanced machine learning functions would need. So for that, we're using Open RAN. And Open RAN, basically in the RAN cluster, has an architecture where you have a data bus based on a technology called Kafka, and you can have different publishers and subscribers, okay, to information in this data bus. So we are developing a set of XApps. XApp is an ORAN terminology. So small control plane applications that are going to be gathering the detailed telemetry for each UE, for each cell on the 5G side, on the Wi-Fi and on the Li-Fi side. And we're going to be publishing and making all this telemetry available in this bus, so other applications can come, tap on the telemetry, and apply the intelligent actions. One such application that we have in the project is what we call this 83S controller, that it's, for example, going to be modeling how people are moving in an environment, and seeing, for example, if the Li-Fi coverage is going down, which is something that happens very abruptly in Li-Fi scenarios. So we're going to predict that, and very quickly we're going to tell the 83S function to steer the packets through other technologies, avoiding Li-Fi. So this is an example of how having data can allow you to build these advanced control plane applications. So that was, let's say, some highlights about our multi-connectivity framework innovation. What I'm going to describe now at a high level also is our notion of infrastructure slicing. So you remember I said that the technology we developed allows us to deploy infrastructure slices that then can be used by different tenants. An MNO could be a tenant, but also hyperscaler could be a tenant, a connectivity service provider could also be a tenant, or the same private venue owner. So this diagram in an abstract way represents our infrastructure. So we have the radio heads, the 5G, Wi-Fi, and Li-Fi here. We have our RAN cluster, and we have the compute cluster. First thing to notice is that we can segregate compute resources into what we call compute chunks. So we have a segregated compute resource here with defined RAM, CPU, and storage, and we have a 5G core instantiated. And then that's going to be used for the private venue owner. And then we have another compute chunk that can be used, for example, to host an MNO slice. So in the first slice here, what we could do is, okay, I want to deploy a user plane function to have access to this virtual application 1. And this virtual application 1 should be reachable from these two 5G small cells under this slice identifier, SSD, for those who are familiar with the 3GPP terminology, but will also be available and reachable through Wi-Fi under SSID1 and also through Li-Fi under SSID1, okay? Inside the same, let's say, 5G Clarity infrastructure slice, we can deploy a second 3GPP slice with a dedicated UPF and another application, virtual application 2. And then we're going to make this one reachable only through the first small cell, not the second, with this slice identifier, and also through Wi-Fi, but not through Li-Fi in this case. And finally, we can also, or the MNO, through this capability exposure that Jose was introducing in his talk, could deploy another dedicated slice here with a service, a dedicated UPF, and this one would be available through this small cell and through the yellow SSID here in Wi-Fi and Li-Fi. So this is the flexibility that we are trying to bring to the management of these private networks. This is all made possible through the 5G Clarity Service and Slice provisioning subsystem. Okay, so this was about our slicing innovation. So moving forward, I'm gonna give you some highlights, brief, about the hybrid positioning approach, because after me, Jesus will give you really an in-depth introduction to our positioning technologies. So I think the highlight for positioning is that what we do is hybridize, okay? We are not putting all bets into one frequency band, into one technology for positioning, but rather saying, look, there's gonna be multiple technologies, which is inherently our approach, okay? We already have multiple technologies for data communication, so we're also gonna use them for positioning. And here we use a combination of millimeter wave and sub-6. That would be the 5G bands, let's say, using time differential, time of flight technologies and different variants of that. And here you could expect using sub-6 frequency bands up to 1 meter or better positioning accuracy, using millimeter wave 1 centimeter or better, but you need really line of sight between the device and the anchor. Using Li-Fi, you can use RSSI and you can use proximity, but since light is very focused, then you get good proximity resolution. And if you use Li-Fi, there is another approach called optical camera communications. That works only for certain types of receivers, for example, smartphones, or receivers that have a CMOS camera. If you have such a camera and such a receiver, then you can get a centimeter level accuracy as well by using Li-Fi to identify some landmarks that are then used by the device to position itself in the 3D environment. And finally, it's about hybridizing these different technologies and having a single positioning server that can provide an enhanced positioning accuracy out of the measurements of all technologies. Okay, so this was the summary of the main innovations that we bring from the 5G Clarity side, and I will now explain where are we applying this and the use cases that we're developing in the project. First one is what we call our smart tourism pilot in the city of Bristol. So maybe several people in the audience know this. So this is the M-Shed Museum in the Bristol waterfront. This is an image of the museum. And the idea here is the use case will be designed around the figure of these robot assistants, okay? We're gonna deploy our various technologies and our slicing subsystem through in the museum. So we'll have Wi-Fi, Li-Fi in some places, 5G NR, one 5G NR small cell. We're going to have some cameras that will assist in the positioning of the robot connected to this infrastructure. And we're going to have the robot with what we call the Clarity CPE and the multi-connectivity framework connected through the three technologies. So then this robot will be used in different simultaneous use cases, like it will welcome visitors and guide them to the point of interest. But it can also be used for other on-demand surveillance activities, or for example, to serve third-party content. Okay, if you are organizing an event in the museum, you could onboard third-party content into the robot that could then be offered to the visitor. So that's how we're going to demonstrate the use of our technology in a museum. That is an interesting example of a private venue deployment. The other two use cases are focused on a manufacturing environment. So this is a factory that Bosch has in Aranjuez, which is a city near Madrid. And this explains the situation that we have for the first use case that we have at the moment. So today they are connecting, they have what they call MES enabled production lines. MES stands for Manufacturing Execution System. Okay, and the idea here is that you have a production line. Okay, there is a conveyor belt and there's a set of working stations, and you have a PLC controlling each working station. So the way it works with today is the PLCs send information to the MES, which is like the operative system, and the MES sends commands to the PLC. If something goes wrong here, and these commands are lost, the production stops. So there's an economical impact of this. So there is Ethernet connectivity being used at the moment, okay, where you have separate VLANs, one for each assembly line, all connecting the assembly lines in the shop floor to the technical room where the MES servers are located. Okay, so what we want to validate from the 5G Clarity is the possibility of doing this, getting rid of this cabling, of this Ethernet cabling that connects today the assembly lines to the technical room, placing our smart connectivity framework and our CPU with the 3 different interfaces, connecting our wireless technologies around the shop floor, and connecting assembly lines using wireless instead of using wired. What this will bring into the Industry 4.0 environment is then the possibility of reassembling and reconfiguring these production lines in a with much more agility than what it's possible today. So that's our first use case in the factory environment. And the second use case in the factory environment is about positioning. Okay, in the factory environment already there is an increasing use of AGVs, so automated guided vehicles. This is an example of the model that's being used currently. And what happens with this is there is a manufacturer, in this case I believe it's Fujitsu, that provides this AGV, and they have to train the AGV to do a specific route. Okay. And that has been done, and the AGV is in production in the factory. But then the AGVs have sensors, and if someone is crossing, the AGV will obviously stop, or the AGVs might be stopped or might deviate from this planned route for reasons that the factory owner does not fully understand today. So the goal of the use case is to really have this very detailed understanding of what the AGV is doing at every moment. And for that, we're going to use let's say, aftermarket solution. We're going to put place our CPE on top of the AGV, and using the positioning technology that Jesus will explain later, we'll be able to track and follow very detailed the movement of the AGV, so that Bosch can then study how often does it stop, why is it stopping here, maybe they need to reconfigure the route, or maybe they need to reassemble the factory in some way to make all this process more efficient. Okay, so to conclude, some takeaways and also some pointers if you have additional interest on the project. So what is Clarity developing is a system for what we call beyond 5G private networks, where we use this combination of access technologies, 5G NR, Wi-Fi, and Li-Fi, provide the smart connectivity and the positioning, okay? We have our concept of slicing or infrastructure-based slicing to enable multi-tenancy in private networks. There is a lot of focus also in the P&I integration and developing these new service delivery models between the private and the public network. And then there is all the aspect of AI and intent-driven control, which we have not discussed in detail today, but there is a lot of work in the project on this, with 9 machine learning use cases being developed. The use cases that I explained will be demonstrated in the Q2 next year. And I just leave you here some deliverables and documents that have been published by the project in case you have interest. So with this, I thank you and I conclude my talk, and Mir, back to you. Hello, Mir.
I think he's just had a connection issue. He's just rejoining now.
Okay,
right.
I froze for a second, thinking I had been speaking for half an hour without no one hearing me. Okay,
we heard you.
Apologies, I was kicked out of the Zoom session for some reason. I don't know what was that. Just a couple of minutes ago. Thank you very much, Daniel, for your total presentation on 5G Clarity activities, innovations, use cases, and also informations. Thanks a lot. I don't see any question to Daniel at the moment. You can post your questions to any of our speakers into the chat box. Please do so. And I have lost the history of the questions. I don't have them anymore. But we can go ahead with Jesus' presentation on localization in private networks using RAT-independent technologies.
Yes, Mir, thank you. I guess you've seen my slides already.
Yes, I can see.
All right. So, hi everyone. My name is Jesus Gutierrez. So I'm the project manager at IHP. For those who do not know, so IHP is a German-funded research institute that is particularly interested, at least from our side, from our group, in building up circuits and systems that make use of circuits and systems for high frequency that are being built in our institute, in our fab, which is here on my right-hand side. So we start with the motivation. Wait a second, I need to. Okay, so now. So the thanks to the speakers that have spoken before me, so it's a bit more easy to raise the motivation. So we are in private networks. We consider private networks in 5G clarity, and we feel and we see the need of more robust, versatile, and high accuracy positioning techniques. So we are talking here about Industry 4.0. We understand that these techniques are either employed outdoors for many applications and making use of or providing these services to more particular or vertical related services. As well, this happens in private networks and particularly in industry. Together with positioning techniques and also apart from some other developments like Wi-Fi sensing and so on, there is a need of having a reliable distribution of synchronization references throughout the network. So this benefits many vertical sectors. This benefits many services provided by vertical sectors that belong to different or map to different 3GPP service classes. And then at the same time, they improve positioning results. So the use of increased precise synchronization reference will benefit indeed the positioning. If we talk about 3GPP, for example, 3GPP Release 16, of course, we can talk about Release 17. So the goal was to achieve indoor positioning below 3 meters using 5G new radio. Of course, these 5G technologies and 3GPP allow the inclusion of additional technologies that may support wider bandwidth, beam-based systems, of course, making use of beamforming, and as well higher spectral efficiency with higher numerology for 5G. The point here, or one of the main things here, is that these technologies, or part of these technologies, are provided by 5G Clarity, as we talked later. So it's Li-Fi, Wi-Fi, millimeter wave, and sub-6. Not particularly Wi-Fi, but sub-6 technologies can be used here. Then another point in which 5G Clarity leverages is the cooperation between access points, as Danny mentioned before. So we have different technologies, and we can make them cooperate to achieve even a more accurate and precise positioning result. And there are two open questions still that are to be studied. So this project may be a good place to take a look at these 2 points. So it's how the nodes are distributed within the serving area, and which impact does it have on the positioning accuracy. So of course, when talking about, for example, this Bosch factory that that Danny mentioned in Aranjuez, we have different possibilities on how to deploy these technologies around the factory, and of course the way we position these technologies and the amount of technologies we bring impact the positioning accuracy. As well, there is another impact, which is a trade-off on how accurate position estimation can be and how complex and costly the positioning deployment is. So this kind of these two reasonings are interrelated. The more technologies and the more units per technology we provide to a certain environment, probably the more accurate the position will be. So continuing with the approach already mentioned by Daniel before. So 5G Clarity will provide centimeter level localization capabilities leveraging synchronization methods. So that means we will have centimeter level localization, I guess, for most of the time, 99.9% of the time. So we are considering mobile environments. We are considering different technologies that have to cope with this kind of harsh environments that are normally indoor environments, talking about, for example, reflections and non-line of sight, signals arriving to the receivers and so on. And for that, we use several technologies. Each of them have different particularities, different bandwidth, different, let's say, resilience to blockage and some other factors, which are sub-6. In this case, particularly for positioning, we use ETU's commercial equipment as sub-6, as they can be configurable in frequency. We have a proprietary IHP's millimeter wave solution, which has been built in-house, both from the baseband and MAC pads and as well the RF pad. We have Li-Fi provided by University of Strathclyde and pure Li-Fi units, and we have the work from I2CAT on optical camera communications. In addition to this, we are particularly interested on providing PNFs or VNFs for synchronization, and that are considering both cases, joint synchronization and positioning developments, which have been already published in the past. So there is some state of the art on these technologies, but we are trying to combine the world's synchronization, positioning, and artificial intelligence, machine learning. The fundamental synchronization requirements did not become more stringent in 5G, indeed, but there is a need for time synchronization, and this has become much more critical. Some other new developments are there, like, for example, this use of PTP 1588, which is there for some long time, but they are revising the versions. There are some other hardware supporting particular implementation of 1588, which is White Rabbit. So these two are for wired communications. And then, of course, there is the possibility of using radio-based synchronization using time-of-flight-based schemes that are already being used for positioning. So in this case, the simple strategies with the different techniques we have for 5G and some other technologies for positioning can serve synchronization and the other way around. Having said this, I will not stay much in this slide, as this was presented by Danny. So the idea is to provide different positioning technologies. On one hand, we put together millimeter wave and sub-6, as there has been some previous work in this sense, where sub-6 provide some support to millimeter wave in providing assistance on fast, let's say, tracking of where the pencil beams of millimeter wave are steering, so that favors the alignment for millimeter wave. So the methods are known methods that are also used in 5G, like DLTDOA, ULTDOA, or even two-way ranging. There are some methods that require tight synchronization schemes, wired synchronization schemes, like the DLTDOA. There are some other schemes that do not need that wired synchronization, but leverage wireless synchronization, like two-way ranging. So the expected precision is 1 meter or better for sub-6, and the one for millimeter wave is 1 centimeter or better. For Li-Fi positioning, in this case, Li-Fi based on received signal strength, and we have two different possibilities here for bringing in results from this project. So one is fingerprinting, the other one is RSSI as such. So Li-Fi is expected to have a precision of 1 meter or better, but they have a limited, let's say, range when compared with RF-based technologies. On the other hand, we have, as Danny mentioned, optical camera communications, which make use of Li-Fi lights that are being detected by CMOS cameras present in some smartphones. And the lights are modulated, and we can decode the light and then make a map 2D, 3D to know exactly where the user is placed within that room. And then finally, the idea is, and then the word hybrid is because we are developing a positioning server which is able to retrieve the information, the estimates, position estimates from each of the technologies, and there will be some functions there involving ML, AI, that would be, let's say, desired to provide a more precise, more accurate positioning results at the end. Going fast through the different technologies. So for the sub-6 technology, we can have some Wi-Fi, so IEEE 802.11 implementations that use a large channel bandwidth up to 160 megahertz with sub-meter precision. But this entails a lot of overhead. There is a lot of signals coming in and out in the Wi-Fi standard, basically. So we have decided to reduce a bit the workload and the different overheads associated to Wi-Fi to use either one that we have in-house, which is ultra wideband, and the other one, which is the one that we are finally using in 5G Clarity, which is sub-6 gigahertz TDOA based on Etus equipment. So we are using USRPs N321 that support White Rabbit, so this implementation of 1588. For this DL-TDOA, for example, we need the anchor points to be synchronized. So either we use 1 PPS 10 megahertz reference signal, or we use this White Rabbit protocol as such. So for this, you have to make use of a White Rabbit switch. And we are using the 5 gigahertz band for this and 160 megahertz bandwidth. So we have done, as part of the preliminary work for one of the work packages in 5G Clarity, we have done a study, a demonstration in an indoor environment with 6 of these USRPs. So we have up to 7 USRPs, although here we plot only 1. So there would be 6 anchor points and 1 user equipment in the middle that you see here. And all of them are USRPs indeed. All of them are synchronized via cables, and we are considering a room of 10 meters by 22 meters. The positions here in red, these red circles are the position of the anchor nodes, and the user given us a coordinate system is moved around the room and allows us to estimate the position. So we see here on the right hand side the anchor nodes here in black, and in red the different position of the user equipment. And you see all those clouds around, which are the estimated positions using these techniques, basically DL-TDOA. When analyzing the error of the position estimates, we see that for this sub-6, I insist 160 megahertz, we see that we stay below 20 centimeters. Moving to the next technology, also brought by IHB in this case, it is the millimeter wave technology at 60 gigahertz with a proprietary solution. We are using 2 gigahertz of bandwidth, and the goal is to have a sub-centimeter level positioning precision. So for this, we have used this baseband and MAC modem, which is able to provide the baseband signals to us for the processing. Additionally, we could use an automatic gain control. So we have 2 nodes here separated from each other at distance d. As soon as you separate these nodes, of course, the received signal strength is not that high, and because of the lack of this AGC, the position estimates may be a bit affected. But this is the setup that has been used here. Whenever we see the true distance versus the estimated distance for this case, we see the true distance in blue and the estimated distances with the red cross, and we see that they match almost perfectly that separation up to 5.5 meters, which has been the measurements. Then on the right-hand side, we have the empirical CDF of the error of the distance measurements, and we see that for most of the measurements, we are quite below 1 centimeter, and for the average of them, we are around 1 centimeter, basically. This is a static scenario, by the way. Then moving to the Li-Fi technology. So Li-Fi APs usually, as I mentioned before, usually have a much less coverage than that of RF techniques. So we rely on RSS, as I mentioned before, and we have 2 options here. So one is to rely on the distance, making trilateration calculation, and the other one is fingerprinting. So for this particular case, we are providing here fingerprinting. We see here on the left-hand side an RSSI measurement using a Li-Fi dongle as the UE. So these are the Li-Fi dongles that for, let's say, signal power reasons are oriented vertically in order to have a good connectivity with the LED, with the light on top. So these are the positions of the UE locations in blue, and this is the position of the source. We see here in ABC a different representation of the RSSI. So here we see the RSSI counting on the different coordinates and the positions of the UE in 3D. Here we have the same representation but in 2D, and in the figure C we have here a representation of the RSSI versus the link distance between the AP and the different points of the UE. On the lower part of the figure, we have the same case of study, but in this case, it's involved the movement of the Wi-Fi dongles, as we see here with this pattern. And in this figure on the right-hand side, we provide the RSSI values measured as the different, as the dongle moves throughout this path. So reaching the optical camera communications, this is work done by I2CAT. So it relies on visible light positioning. So as I mentioned before, it is about modulating light sources, which light is detected by a CMOS camera on the other side, and it decodes this light ID, and it's able to make a mapping from 2D to 3D. So for this, the CMOS camera obtain centimeter level accuracy when light fixtures that are at the ceiling transmit a known identifier. And this light features, the requirement here is that they have to allow for switching modulation so that the CMOS camera is able to detect. The CMOS camera does not analyze the full picture at the time, but it analyzes pixel columns that is detecting one at a time. One of the most important things here is to do the mapping from 2D, from the photo captured by the CMOS to the 3D space, which is here, a mock-up scenario, let's say. And then we see here that we can achieve for 90-something% of the time with 6 lights that we use for the demonstration, as we show here, we can achieve up to well less than 0.55 centimeters, so much less than 1 meter. Then, having all the technologies explained, we have the so-called localization or positioning service. This defines the interface towards the WAT. So it's a wireless access technology provided before has an interface to this localization server. So is in charge, the localization server, of controlling the positioning functions and to merge the different positioning information into a single position estimate. So there are functions being developed that incorporate all the estimates from each of the technologies and provide a new position estimate. So for that, we use fusion-based approach, for example, by using recursive filtering, which is able to achieve, if we see here the blue line, a much more precise positioning when compared with the ones done by the others. And finally, one of the last slides that I have is the use of machine learning for end-loss awareness. So we are in an indoor scenario in a factory. In this kind of scenarios, we have a lot of reflections, a lot of multipath. So we would like to understand whether the first channel tap or first, let's say, communication rate that we have, it's indeed the one that we have to use for localization. So we have to discriminate whether that belongs to the direct path line of sight or that belongs to the non-line of sight path. For that, we use deep neural networks and support vector machines. So we have done this in the past, and we are here comparing results for this kind of, let's say, scheme. So we have an endpoint FFT and loss identifier and different ranging capabilities. So we train data for NLOS, we train data for line of sight, and we provide here for this office hall that we see here with the different positions, we provide a comparison between NLOS detection from the support vector machine side and from the deep neural network. So this is being now produced, and more details will be provided in a deliverable called T4.2. So finally, all this work will be integrated in each of the labs. So each company, each partner providing the technology will be providing different results for each technology. At the end, we will all come to this factory in Aranjuez with these units and associated developments, methods, techniques for positioning. And the idea is to provide centimeter level precision localization for this AGV that moves around the factory. And as Daniel mentioned before, so Bosch is not able yet to understand what happens as the AGV moves across the path. And the idea is to understand whether there might be some emergencies, there might be some places where the AGV has to stop. And we, 5G Clarity partners, are in charge of recording that and providing this information to the factory. And with this, I arrive to the conclusion. So 5G Clarity makes use of different wireless access technologies to reach this sub-meter positioning. Synchronization is key to achieve optimal positioning results. So all the measurements that you have seen here will be assessed using wired synchronization and wireless synchronization for the sub-6 millimeter wave using White Rabbit, for example. And the deployment design has a significant impact on the positioning performance in terms of both accuracy and availability of the service. So this has to be assessed as well in each of the labs, and at the end assessed as well what is the impact, probably with in a simulation environment, or finally in the Bosch factory at the end. And then we have shared that machine learning and artificial intelligence are useful techniques to support positioning. And at the end, yes, 5G Clarity will be assessing the hybrid positioning approach at a trial in a Bosch factory in Spain. So that was my presentation. Thanks, everyone.
Thank you very much, Jesus, for your presentation on the indoor localization with a specific look into the private networks. So with this, we have finalized our presentations. My apologies, as I have to turn off my video. I was kicked out of the Zoom session a couple of times. Then I decided to turn off my video. Please post any question you have into the chat box now, as we have a few minutes left for discussions. We already had a couple of questions in the chat box which were answered there, but maybe I'll ask again, Jose, to re-express the question, your answer to the question of the operator's role in NPN, where you categorized that, and the question was if there are any other types considered for the operator's role in NPN. Jose, are you there?
Yes, I'm here.
Oh, okay. That would finish this.
Can you please mute your mic if you're not speaking? Thank you. Jose, please, yep, go ahead.
So could you repeat the specific question again, please?
Yeah, the question was in the chat box, and you answered it already, but I thought maybe not everybody has seen your answer, so you may want to elaborate on that discussion now for us.
Yeah, so, well, there was a question on the problems with qualified staff that will run, manage, and maintenance private networks. So as I said before, the real challenge is to integrate very different technologies together and operate them in a unified way. So that's maybe the new major change compared to the private LTE networks that exist for some time. And there was also another question on the how do we see the ORAN market here in the public mobile net in the private mobile network. Sorry, and I totally second Danny's answer on this question. We expect to have ORAN first integrated in standalone NPMs, in local small scale private networks where innovation and introduction of new features is much easier. And then when the operators get the know-how and had some insights on how to operate this together, then we can think of introducing ORAN features in the public network, trying to bring the real advantages of this technology into for our end customers to facilitate and open also the operation of our networks and to get it deployed at a much large scale, which at the end of the day will be the enabler to reduce costs, right? And that's basically the operator's view on the ORAN issue.
Thank you very much, Jose. Any complementary discussions from other experts on these two?
Maybe here on the ORAN issue is what we're seeing in private networks is, I mean, at the end, the ORAN, I think, key point is the compatibility between Radiohead vendors and base station vendors, okay? And vRAN vendors, let's say, because you can get an ORAN solution with a standard Dell PC, for example, with a CPRI card, a radio stack running on CPU and the Radiohead. But there is this interoperability between the stack and the Radiohead. And let's say the Radioheads that we see relevant in the NPN domain, it's maybe for outdoors, you have like 5 watt, 44R, you know, but you don't need much more than that in most of the use cases. Then you have indoor deployments where you have this type of radio dot, but radio dots are also 2T2R typically. And let's say there is more offering now in the ORAN space on the support for these more simpler Radioheads than the very complex massive MIMOs that you need really in public networks for 5G. So my personal feeling is in the massive MIMO Radiohead domain is Ericsson, Huawei, Nokia, they have technology that no one else has at the moment. And that's why I think what's really slowing down ORAN adoption in the public network.
Okay, thank you very much, Daniel, for complementing the answer to this question. We didn't receive any further questions. If there is not any comments from our experts, I think we are about to end our panel here. I would like again to thank you all for your excellent presentations and discussions here, and I'd like to thank 5G Week for this opportunity for us to have this panel here, and also for also thanks to the audience to attend this this panel and be with us during these presentations. Thank you very much, and I wish you all a good day.